last video, we had derived the Bernoulli's equation. Now, in this video, we will see few applications of Bernoulli's equation. First application is the Ventury tube. Second is the aspirator pump. And third, we will determine the speed of efflux. So these three applications we are going to see in this video. First application, the Ventury tube. The Ventury tube is used to measure the flow speed of a fluid in a tube. We will consider in this diagram, we can see the Ventury tube through which a liquid of density rho is flowing. This tube consists of a constriction here. You can see a narrow part, or we can call it as a throat, a constriction or a throat in this tube. So because of this constriction, the pressure decreases as required by the Bernoulli's equation. This wider part will have an area of cross section which will denote as A1, and the constriction part will have an area of cross section A2. We will denote the speeds. In this area of cross section A1, we will denote the speed as V1, and in the constriction part we will denote the velocity of the liquid as V2. Same way, the pressures in the respective area of cross section will denote as P1 and P2 respectively. So as the fluid passes through the constriction, the speed will increase. This is in accordance with the equation of continuity which we had derived in the first part or the first video of this series, which you can go and check. That was the equation of continuity is given as A1 into V1 is equal to A2 into V2, from which we had seen that the velocity of the fluid is inversely proportional to the area of cross section. So as the area of cross section decreases, the velocity increases. So hence in this constriction part, the velocity is increasing, and hence we can say the pressure decreases. Now we will write the Bernoulli's equation for this tube. That is, for this area of cross section A1, that is denoted by LHS, and for the area of cross section A2, we are writing it in the RHS. So that will be P1 plus half rho V1 square is equal to P2 plus half rho V2 square. We can take P2 on the other side, so that would be P1 minus P2, and this term we can take on the other side on the RHS, so that will be minus half rho V1 square. By taking half rho common, we can write down this as half rho into V2 square minus V1 square. Now the figure shows these two vertical tubes that are connected to the Ventury tube. These tubes are connected at A1 and at A2. So there will be a difference in the heights of the liquid levels, which are shown over here. Here the liquid is filled till this level, and here the liquid is at this level. So that both the liquid levels are at a height h. It's written here. So we will write down the pressure difference, that will be P1 minus P2 is equal to rho GH. So now we will substitute this pressure difference P1 minus P2 in this equation which we have got in the earlier slide. So rho GH is substituted here. And now rho will get cancelled out, and you can take the term or this 2 on the other side, so that would be 2 rho gh is equal to v2 square minus v1 square. So we have derived this formula. So from this formula we can know the rate of flow of the liquid past a cross section. Second application is the aspirator pump. The figure is shown. So when the fluid passes through a region at a large speed, then the pressure there will decrease. So this principle is used in number of applications. So we'll see one of the application, that is the aspirator pump. In the aspirator pump, you can see this barrel, this yellow part which is denoted by A, which contains the air. It terminates in a small constriction which is denoted as B. There is a narrow tube C which connects this constriction B to a vessel. It contains a liquid that is to be sprayed outside. So now there is a piston inside this barrel A. The air in this barrel A is pushed by the operator with the help of this piston. As the air passes through this constriction B, its speed will be very high and hence the pressure will drop. And due to this reduced pressure in this constriction B, the liquid is raised from this vessel D and it is sprayed with the expelled air outside. Third is the speed of efflux. We will consider a liquid of density rho filled in this tank that is shown in this diagram. This is a tank having a large cross-sectional area A1. There is a narrow hole here which we can call as an orifice. It has an area of cross-section which will denote as A2. This hole we are denoting at this point B. And the top surface of this tank we are denoting as A, or the surface of the liquid, top surface of the liquid we are denoting as A. So the liquid will flow out of this tank through this hole. So now the pressure at surface A and the pressure at B, as they are both open to the atmosphere, the pressure will be equal to the atmospheric pressure, which will denote as P0. So we will write down at surface A the respective pressure, height and the velocity. Pressure P1, H1 and V1. Pressure P1 will denote as P0. H1 will be, see, you can see that this part B is at a height H, and this height we are denoting as small h. So the height of this surface, that is the surface A, will be at a height of h plus h, and the velocity is equal to 0 at this point at the surface. Same way for the surface B, we'll write down the pressure P2, height h2 and velocity V2. Pressure P2 is the same, the atmospheric pressure P0, height, this part hole is at a height h, and the velocity V2 we are denoting it as V, which we call as the velocity of efflux. So now all these values will denote in our Bernoulli's equation. In the Bernoulli's equation, we will substitute it. This is the Bernoulli's equation. So P1 is substituted as P0, H1 is substituted as H plus H, V1 is substituted as 0, P2 is substituted as P0, and H2 is capital H, and V2 we are denoting as V. So now here P0, P0 will get cancelled out. We can open up the bracket here, rho g into h. This is rho plus rho g into small h. Again, we observe that this h rho g and h rho g will get cancelled out, and what remains is h rho g is equal to half rho v square. Again here rho will get cancelled out. So what remains is this v square is equal to 2, you can take on the other side. So v square is equal to 2gh. Taking the square root, we get v is equal to square root of 2gh. This is the velocity of efflux. Velocity of efflux is said to be the same as that of a particle which is falling freely through the height h under gravity. This is called as a Torricelli's theorem.